Alright, tonight I'm just going to go through like 3 regents and just pick questions that come up repeatedly that are good to know, and that's it. It won't take very long. I'm not going to go through an entire regents, but let me just send this out on mine. So, reminder, your test is Wednesday at 8 a.m. All right, Wednesday at 8 a.m. What I'm going to do is I'm going to go through January 2018, August 2018, 17, and June 2017. So the 3 most recent chemistry regents. And just pick random questions that repeat often and just go over those. So you can feel free to I'll try to take it slow in terms of giving you time to read the question. So if you're like, oh, I think this one's B, before I go over it, just so you have time to process the question, and hopefully I won't rush too fast. But I'm going to just do this for 30 to 45 minutes, get through as many as I can. For all I know, I might just stick on the January 2018 and just, again, point out very popular, big topics that are on the Regents year to year to year. So we'll get started, and we're going to get started immediately with question 1. So atomic structure pops up constantly. It's always the first 4 to 5 questions on every Regents that I've ever seen, and they're always about protons, neutrons, and electrons in some way. They might get into the history of the atom with Dalton and Thomson and Rutherford and Bohr, but what's guaranteed is a question like 1. Some question that's talking about atoms, ions, protons, neutrons, electrons, isotopes, stuff like that. So as you read question 1 here, the first thing to point out is the fact that it says helium doesn't really matter. They just throw that in there. It's not really a trick, but maybe they're trying to just get you to think outside the box a little bit when you don't have to, or get you to overthink it. But really the question's asking what is true about the location of protons and neutrons in an atom. And what is true about them is answer choice number, drumroll please, 1. So, what are some other variations you'll see on this? If they throw in electrons, which they will from time to time, those are outside the nucleus. Sometimes they'll throw in charges with this. So the nucleus is positively charged because that's where the protons are, because protons are +1, neutrons have no charge, and electrons down here are -1. So they'll throw in a charge from time to time, but I can pretty much say the first question on the Regents Wednesday is probably going to be something about the atom and something about protons, neutrons, and electrons. All right, question. I might come back to 3. I might, but again, questions dealing with ground state and excited state come up often. A question like 4 will be asked in a variety of ways. So it's asking about group 15 atoms. So right off the bat, before I even finish reading the question, I'm just going to familiarize myself with group 15. And if you go to group 15, what the question was asking is what do they have in common? So this gives us a good opportunity to just go over what are the various parts of the periodic table we need to know. And I'm just going to say these out loud because I don't have a lot of room to write. But we have atomic number 7 here for nitrogen. That's protons. So that's in green. Orange up here, that's the atomic mass. So on the periodic table, that's the average of all the isotopes of these atoms. But at the end of the day, atomic mass is all about protons and neutrons. Highlighted in red is the electron configuration. So this is how many electrons are in the atom of nitrogen and where they are. And then highlighted in, let's do blue, are all the various oxidation states, which only come into play when we have a bond, okay? Only come into play when we have a bond. And as you go up and down group 15, what you should notice they have in common is they all have this number 5 at the end of their electron configuration. So, when we go back to the exam, they have the same number of, not shells, all right? Nitrogen has 2 shells. It was 2-5. When you go down to phosphorus, there was 3, then 4, then 5. Since all their masses are different, we know they have different neutrons. And since all of them are different elements, all elements have a unique number of protons. So the right answer here was valence electrons. How else will you see this question? I think this was a more straightforward way of asking this question. A lot of times they go with similar, as a short answer or multiple choice, chemical properties. They're like, in terms of atomic structure, why do all atoms in group 2 have similar chemical properties? Or in terms of electrons, why do all atoms in group 17 have similar chemical properties? Or in terms of electrons, why do all the atoms in group 18 not bond, or have a tendency to not form bonds, or have a tendency to not react with other elements? And that is because in every group, when you look down every group the periodic table has, they all have the same number of valence electrons. So if you look at group 13 here, we got B, 3. Aluminum has 3. Gallium has 3. 3. Group 12, 2. 2. Mercury, 2. Every group has the same number of valence electrons, which means they have similar bonding properties, which means they have similar chemical properties. Yeah, 5, just knowing how to do chemical formulas is going to pop up Regents to Regents to Regents. All right, molecular polarity. That's going to come up in some way from year to year. When you see polar versus nonpolar, you just want to think SNAP. In terms of the molecule polarity, you want to think SNAP. So symmetry means it's not polar. Asymmetry means it's polar. So what I would do here is cross out the answer choices that don't match with the acronym SNAP. So we want symmetry nonpolar. So that says polar is symmetrical, which is not true. And this says nonpolar is asymmetrical, which is not true. So this one's a little, I would say, harder than usual. Usually, if you use that SNAP acronym, you could just narrow it down to the right answer pretty quickly. Here you have to draw it. So this brings up a good opportunity to review drawing, because you're probably going to have to draw a dot structure of something on the regions. The way I do it is I have my kids get all the atoms individually. So we have a carbon, an oxygen, and an oxygen. And I just have them draw their individual dot structures as atoms. So if I look up carbon, carbon right here has 4 valence electrons, and oxygen has 6 valence electrons. So when I'm going to go draw carbon and oxygen on their own, I'm going to draw carbon with 4 dots. All right, 1, 2, 3, 4. And oxygen with 6. And based on what I can see, carbon has 4 dots that are looking to form a bond, and each oxygen has 2 dots looking to form a bond. So we're going to throw those dots together. Oxygen had its 2 already paired, 2 ready to pair with carbon, who had 2 to share. And again, the same thing over here. And you could also have drawn it like this. It's because when you share 2 electrons, they are going to form a bond. When you share two pairs of electrons, or four total electrons, like here, we have four electrons being shared here and here, that's going to form a double bond. And when I look at this carbon, I don't see any lone pairs on it. I don't see any dots on it. All the dots carbon did have are now in a bond, which means this is symmetrical, which means the answer here was nonpolar and symmetrical. So polar and nonpolar are going to pop up a lot. This molecule, though the molecule is not polar, if you have two atoms that are not the same, you would say these are polar bonds. So a polar bond just means two different atoms bonded together. C and O, H and O, H and N and F, O and F, whatever. If they're two different atoms, you have a polar bond. If they're two different atoms and they're both nonmetals, you have a polar covalent bond, because nonmetals form molecules and the bonds within a molecule are covalent because they're sharing electrons. So these share electrons here because they are both nonmetals. Now, if you had a metal and a nonmetal, I know we're getting a little off track here, but all this stuff is important. If you have a metal and a nonmetal, let's say sodium fluoride, so NaF, we have a metal and metal. That forms an ionic bond, and ionic bonds transfer your electrons. So ionic bonds are metals and nonmetals. That involves a transfer of electrons. So we wouldn't say, though really technically yes, this is polar because one's very positive, one's very negative. We don't describe your ionic bonds as polar and nonpolar. We just describe them as ionic. If you have two nonmetals, they can have a polar bond, they can have a nonpolar bond. If they're two different atoms, they are polar bonds. If they're the same atom, like oxygen with oxygen, or F with F, or N with N, that would be a nonpolar bond. But no matter what, covalent bonds share electrons. So all of these ones below, these two carbon dioxides I've drawn, have covalent bonds because they are nonmetals. So that pops up year to year. Again, I'm going to piggyback. I don't want to spend too much time on each question. I don't want to review an entire Regents. It's just going to take too long. I posted on my website reviews from your review book. Though your review book has answers with explanations that you can practice, someone on YouTube has posted videos going over all four of those Regents. And it takes them like 2 hours because it just takes a while to go through these. So I'm really picking and choosing here the big ones. All right. Bonds breaking and bonds forming. Huge topic. You're going to remember BARF. Breaking a bond absorbs energy. So breaking a bond absorbs energy. Releasing energy forms a bond. So the first thing you want to do as you're reading this question is say, is a bond being formed or is a bond being broken? Meaning, is one thing breaking apart and forming multiple things, or are multiple things forming a bond and becoming one thing? And if you can't remember the acronym, when they give you this equation, you should be able to eliminate two answers right away. Because when I see this equation, I see two oxygens becoming one molecule of O2, which means a bond's being formed. So I'm going to cross out the two answers that say bonds are broken. Then I'm going to apply BARF. Breaking absorbs energy. Well, this question was not breaking a bond. It was forming a bond. And when you form a bond, RF, releasing energy forms a bond. So energy here was released. Sometimes you'll get lucky and they'll put energy in the equation. So if energy was put in this equation, you would see energy leaving the reaction. When energy is being released, it's going to be on the right side of the arrow. Everything on this side that I'm going to highlight in yellow means it's being formed / released. So this oxygen, if it's a gas, is being released. It's being formed. It's a product. It's being produced. So energy here is being produced. You would feel that energy being released, typically in the form of heat. So this is a big one. All right, I'm going to do a couple more on this page. I'm going to do 12 quickly because it comes up in different ways every year. Sometimes the question just has you use table S. I just want to make sure that we understand that when it says strength of attraction for electrons, how strong you're attracting electrons, the answer that has electron in the word is what we're looking for, electronegativity. All right, kinetic molecular theory of an ideal gas. We want to pick the answer that's true. And we did this a while ago. I'm talking like October. And I didn't have time to review it in class because chemistry is just, it's a long curriculum. I mean, these are 85 pretty unique questions. So when you do kinetic molecular theory, if you can't remember what makes an ideal gas ideal, first, what's not mentioned in this is an ideal gas. So ideal, if you see this word for gases, that means a high temp and a low pressure. Contrasted with solubility, a soluble gas stays soluble, meaning stays dissolved. That carbonation in your soda or seltzer will stay in that bottle or can if you keep it at a low temperature, put it in the fridge, and a high pressure, keep it closed. Keep that aluminum can pressurized. So an ideal gas and a soluble gas, these conditions pop up. They don't put them both on the same regions because it's kind of, I mean, when you look at this, they're just opposites of each other, so it's kind of mean. But one of them will most likely appear on Wednesday. So ideal gas is like an ideal relationship. It's hot with low pressure. A soluble gas is like your soda. You want to keep it cold and pressurized in that can. So this question is about ideal gases. I'm going to go through answer by answer and correct the wrong ones. Colliding without transferring energy. That's false. An ideal gas will collide with transfer of energy. So when ideal gases collide, we assume they're kind of like a pool ball. It takes that energy from the cue and just throws it into another, whatever ball you're trying to hit. They move in random straight line motions. That is the correct answer in this case. That is true. An ideal gas, as you approach these very high temperatures, will move in random straight line, constantly moving motion. Arranged in a geometric pattern, that is incorrect. That is true of a solid in a way. When you think of a solid, you think of a crystal structure. Think of this rigid crystal structure. When you think of an ideal gas, they're just random. They're not arranged in a geometric pattern. They occupy the size of the container they're in, and they're moving kind of chaotically. They have a lot of entropy. Separated by small distances, that is not true. They are separated by large distances. They're very far apart. They're so tiny, we just assume that they're super far apart, okay? They're so tiny, we assume they're far apart. So, ideal gas, random straight line motions, energy is being transferred when they collide. They are small, very tiny. They're separated by large distances, high temperature, low pressure. Okay, those are some stuff to keep in mind. Catalyst, always going to be involved. There's going to be one or two answers. So I'm going to give you a moment to read this and see if you can figure it out. One of two things you can always say about a catalyst. First, it increases the rate. So a catalyst will always speed things up. Catalysts getting the reaction to go faster. All right? And they do this by taking the activation energy and lowering it. So 4 might have been tempting because a lot of students will remember activation energy as being involved with the catalyst. So they'll be tempted to pick the answer that says activation energy. But it decreases the activation. It does not increase the activation energy. And if that's counterintuitive, the activation energy you can think of, I'll cross out activation and put starting energy. So just imagine it takes pasta, or if you're cooking something, you have to preheat the oven to 400 degrees. A catalyst says, no, you can actually cook this pizza at 300 degrees. Your oven is going to preheat faster. You'll get to put that pizza in the oven quicker, which means you'll be given dinner faster. So, by decreasing that starting energy, by saying, oh, this reaction only needs to occur at 100 degrees Celsius instead of 200 degrees Celsius, the reaction is going to go faster because it's easier to get it to that starting point than originally. But decreasing the activation energy isn't a choice here. So the other wording you'll see is this providing an alternate reaction pathway. And that exact language, like word for word, will pop up year to year to year. They sometimes will morph them together. They say, how do catalysts speed up reactions? Oh, they provide an alternate reaction pathway and lower the activation energy. Sometimes, like this year, they'll just say, provide an alternate reaction pathway. Other years, they'll just say, decrease the activation energy. Or, instead of making it multiple choice, they'll put it in a short answer question, in which case, all you have to say is, provide an alternate reaction pathway, or decrease the activation energy. $16 I'm going to go over, because it pops up often. But I will say that you guys have been much better this year than last year, at least my students. Same number of molecules as 6 liters of chlorine gas. This is Avogadro's law. Avogadro's law is gases, if they occupy the same volume, will have the same number of molecules. So if you have 6 liters of chlorine gas, the one that has the same number of molecules is 6 liters of nitrogen. They might have been trying to tempt you with this moles, because they both have 6. That's just not true. But 16 does pop up a lot. Let's see, what else is big? All right. Let's do 23 and 24. 23, which device requires electrical energy to produce a chemical change? So this is comparing voltaic and electrolytic cells. 23 here. One of them does that, what it says in the question, and the other one does the opposite. And we need to keep them straight. Last year, they asked on a short answer question, voltaic cells. Voltaic cells will do chemical energy. They will take chemical energy and make electrical. So voltaic cells will always convert chemical to electrical energy. An electrolytic cell will always do the opposite, take electrical energy and create chemical energy. Because electrolytic is not spontaneous, and voltaic is spontaneous. 24. Usually what I would say when you see this word areneous acid is to go straight to table K. Because table K is a list of acids. So let's go to table K. Okay, so let me just erase this here, because this is probably when I did the acid base. Okay, so there's table K. You're going to look here. What you're going to notice is that when I go back to the question, none of the compounds in the question are on table K. But what you should notice is that everything on table K has H's. There's that H. So, An Arrhenius acid, how that's defined, Arrhenius acids produce H plus ions. So if there's a question like, what ion makes this an acid? H plus. Which one is an Arrhenius acid? Look for ones that begin with an H. Look for ones that have H's to donate. 3 and 4 are on table L. And table L is a list of bases. So don't say 3 or 4 is an acid. Learn they're on the table that says bases. NaBr doesn't even have an H, so we got hydrobromic acid. All right, another acid-base question. When does a molecule act as an acid? So you're going to see this wording a lot. One acid-base theory, alternate acid-base theory, something where they don't attach the name to it. The one with Arrhenius, so Arrhenius, we just did acids, so Arrhenius base is all about OH. So when you see the alternate theory, when it doesn't say Arrhenius, cross out the ones that say OH. For acid or base, doesn't matter. You have the Arrhenius theory, where he said Arrhenius acids produce H's, Arrhenius bases produce OH's, and then you have the other theory. And the other theory says acids donate H's, bases accept H's. You will also see a H, sometimes they'll say proton. So sometimes here you'll see proton. So there's two acid-base theories. Theory 1, Arrhenius. An Arrhenius acid produces H plus ions. An Arrhenius base produces OH minus ions. So if you see a question about base and ions, think OH minus. If it says other, one, or alternate acid-base theory, acids donate H's, bases accept H's. Well, sometimes they'll substitute H with proton. Excuse me. Ooh. All right. Now, when you get straight to B1, again, the first few questions are going to be dealing with atomic structure. In fact, here, the first 4 deal with atomic structure, which is why, or maybe first 3, 3 to 4, which is why I highly recommend it. I think literally almost every single person on the sheet I gave out with your goal scores, topic to review, number 1, atomic structure. I assigned it to everybody on Castle Learning. Look it over. It's like 50 questions. That's a lot. I just asked it to pick random 50. Look it over, go through it. It'll help you as you go. It's not set to be a quiz. It'll tell you the right and wrong answer as you're going along. Highly, highly recommend you go to Castle Learning and go to atomic structure. Woo. Let's try that again. Atomic structure. And wow, I cannot type tonight. Type? How about write, Mr. G? Highly recommend everyone check that out. Because you just need the extra practice with that. Because there's always stuff going wrong. Alright. As soon as you see the word ion, you have changed electrons. So electrons have changed. In some way. Knowing that electrons are negative, actually, I'll hold off on that. When you see the word ion, neutrons, don't worry about. A change in neutrons, if you change the neutrons here, that equals an isotope. So when you change the neutrons, you get an isotope. When you change the electrons, you get an ion. So, how do you get the charge? Just do protons minus electrons. 7 minus 10, negative 3, negative 3. Some of you are like, but wait, aren't electrons just negative? If I have 3 more electrons, I have 3 more negatives than I do my positive protons. And I would say, yes, that's what I just did. So either of those are acceptable ways. All right, excited state. They love this question. They love to ask about excited state. Pretty much guaranteed. Excited state takes the electron configuration and moves them from one level to the next. So the first 3 groups go 2, 8, 8. If you move these in any way, you're excited. So which one of these is excited? 2-2, this is helium. Not helium, beryllium. That's beryllium's ground state. Most of these are all ground states. If you go to the periodic table, however, you will not see that as the ground state for anybody, because this one's neon, this one's sodium. 221 doesn't exist. If you go to beryllium, which is 2,2, and then head to the next one over, which is boron, you're going to notice boron is not 221. Boron is 2-3. So if I'm 221, I am in excited state for boron, because 221 still is 5 electrons, but I took one in level 3 and just moved it up to the next energy level. That makes it excited. Average atomic mass, guarantee that's going to pop up. You just got to know how to do it. You take these two masses and percents, multiply them together. So this multiplies that way to that, plus these multiplied together, divided by 100. So take the mass and the percent, multiply, plus mass and percent, multiplied, divided by 100. So that's this one. Polar bonds we talked about. Again, everything on here is important. I'm just picking the ones that are very, very, very repetitive. Very repetitive. Increasing collisions. Basically, increasing collisions is very straightforward. Increase temp. Increase pressure on a gas. Increase surface area. Add a catalyst. Increase concentration. Don't decrease anything. Don't decrease anything. Oh, look. Increase in concentration. An increase in volume, that's a decrease in pressure. So as pressure goes down, volume's going up on a gas. And increasing pressure is what we want to do, not decrease the pressure. So that was 50. And I'm sure there's a few more multiple choice, but I want to take some time and go over some short answer. So let's take a peek here. See, you're almost always going to have to draw something. If you're drawing an ion, usually they'll say, draw this ion. It'll almost always be negatively charged. So fluorine, chlorine, sulfur, oxygen. If they say, draw this negatively charged ion, draw whatever it is, give it 8 dots, put brackets on it if you want. There's dots all around that. I know it's hard to see. And then just -1 or 2 or 3, whatever it is, okay? Bright line spectra, 56. How is light emitted? Electrons, that gets rid of that term, move from excited to ground. Gets rid of that term. So, explain in terms of Use the terms. If you don't use the terms, you're just wrong. Even if you don't know the answer, and your excuse for not using the terms is Mr. G didn't know how to answer the question anyway, I don't care. Use the terms. The terms are a hint. The hint here being, say something about electrons and energy states. Say something about electrons and excited to ground state uses the terms, okay? 56 is a big one. Be prepared to balance an equation. Right, we can go over balancing. How do you balance an equation? P4 plus, this one's easy. There's only 2 atoms. Lovely. I love it when there's only 2. All right, right off the bat, P, Cl. Those are my 2 atoms. Draw a line separating your reactants from your products. How many P's do I have? 4. And here I have 1. That's not balanced. Multiply this by 4. You get 4. Put a 4. 2. 12. That's not balanced. Multiply this by 6. And you get 12. Put a 6 there. Put a 1 there if you want. You don't have to. Be prepared to balance an equation. Percent composition by mass of chlorine in PCl3. They like percent comp by mass. If you get a question like this, please keep in mind that there's 3 chlorines in that problem, not 1. So, chlorine's mass, when you look it up, is 35. How do you know percent comp by mass? There's a formula for it. Percent comp by mass. Part over whole times 100. Don't forget the times 100. It's a percent, not a decimal. So the part is the 3 chlorines, which each weigh 35, divided by the whole, 137, times 100. And you'll get probably over 75%, just doing it in my head, maybe close to 80. So they like percent comp by mass. I might go back up to that. Empirical formula. It's strange. This popped up twice on this Regents. It just means reduce it. So if you have C2Cl4, I can divide each of these coefficients by 2 and get CCl2. That's empirical. If you can reduce it, it's empirical. This, we call that the molecular. That's the actual formula. This actually has 2 carbons and 4 chlorines. But the ratio is 1 carbon to 2 chlorines, because I just reduced it. Heat flow. They kind of like this. Generally speaking, whatever the question is, heat will always flow from a hot object to a cool object. Period. If you touch a hot stove, the heat's flowing from the stove to your hand, telling you this is hot. The heat is not flowing from your hand into the stove. There's a Castle Learning question on your Regents diagnostic that asks about air and ice. And so many of you said the ice loses heat to the air. I don't even know how that's possible. Because if you have ice and you leave it out, it's going to melt, which means it's absorbing heat from somebody, in this case, the air. So the air in the oven and the muffin batter. So I'm assuming somewhere it tells you the muffin batter temperature, but if not, we can use some, well, it tells you thermal energy is absorbed when you're baking muffins. So the air in oven, the heat flows from the air in the oven to the batter. That's a big one. Heat flow. Sig figs. One or none. Last year, which was really, really surprising. There's almost always one question. Pressure at the surface of the lake. So we're looking right here. So that 0 in 10. So we're at 104.0. Most students are comfortable knowing that non-zeros are significant. And sandwich zeros, so that 0 in between 104 counts because it's sandwiched in between two non-zeros. The struggle comes with this 0. Does that count? So, if you have a decimal in your number anywhere, what are you doing? You're being crazy. Where's Harper?
Downstairs.
She being the best?
Yep.
Good. This still squeaks, which is surprising. Alright, so, does that 0 count? If there's a decimal in your number, I don't care where it is, beginning, middle, end. You could have written, says 0.1040, 1.040, I'll do this one, 001040. As soon as you hit a non-zero number, when your number has a decimal, circle it and count everything after. Circle, count everything after. Circle, count everything after. Circle, count everything after. 4. 4. These all have 4. 4. 4. Does number have decimal? Yes. Circle non-zero number. Count everything after it. The end. Alright, how do you know this is exothermic? You know that this reaction here is exothermic. Again, look for where energy is. I see energy here. I see energy is being released. I see energy is exiting the reaction. It is exothermic. Equilibrium. 2 things to keep in mind. Rates are equal. Concentrations are constant. Rates are equal. Constant concentrations. One of those will be there on Wednesday. Okay? IMFs. So, at standard pressure, compare the strength of the IMFs in NO2 to the strengths of the IMFs in N2. So, we know that nitrogen dioxide, sometimes reading these blurbs is important, boils at 294. So this has a boiling point of 294. N2 has a boiling point of 77. NO2 equals stronger IMFs. Because it has a higher boiling point. Do I have to say because? No, just as compare. NO2 has stronger IMFs. Because it has a higher boiling point. Well, you don't have to say that. I'll definitely do that voltaic cell in a minute. Let me just see what this last one is. You see unsaturated bonds. It's all about carbon, carbon, double bond. You can even just say that it contains a double bond. You'll be fine. But this compound, sorry I said equation 1, doesn't matter. This compound has a double bond. Unsaturated means double bond. Saturated means all single bonds. Unsaturated is double bond. Oh, excuse me. All right. How can I tell if something's being oxidized and when something's being reduced? Look at the equation. Look at their charges. If charge goes down, that's reduced. Because that means it's like going down is a synonym for reduction. It's getting lower. It's decreasing. It's being reduced. So every single atom, when it's alone, is 0. Unless when it's not in a bond, we assume that the charge is 0. Mg's charge is going up. Zn's charge is going down. So who's getting oxidized? Well, if the charge goes down, it's reduced. Zn's charge is going down. Zn's charge, Zn is getting reduced. So oxidation, I'm going to do both oxidation and reduction because you might see one of each. Oxidation is Leo. Lose electrons, oxidation. Lose electrons, oxidation. Mg goes from a charge of 0 to its charge by losing 2 electrons. How do you know it lost 2 electrons? Because it went from 0 to 2. So 2 electrons were lost. It goes from a charge of 2 plus, gain electrons reduction by gaining 2 electrons and going to Zn with a charge of 0. Gain electrons reduction. All right, I'm going to do another one of these tomorrow because I think that's a good place to call it for tonight. But just like looking over last year's Regents, the June one. Boom, first one. Which one describes an atom? Already talking about the nucleus. Almost the exact question as the January one. Atomic structure, atomic structure, atomic structure, atomic structure, periodic table. What's another one we did? Let's see. Nonpolar bonds. Collisions. The volume question. This was the same question with a different number. Catalyst. Almost the same question. Oxidation and reduction. Arrhenius, acids and bases, spontaneous energy